My background started as a Master 2 in high energy particle physics at the Lebanese University. Then I did a 3 years of PhD at Laboratoire Castle Brussels in quantum physics for hydrogen molecular ions at Sorbonne University. Then I've done 2 years and a half as a postdoc researcher in quantum chemistry at Sorbonne University in collaboration with Total Energy and Atos in France. And currently, I'm holding a position as a senior researcher in quantum computing at Qubit Pharmaceutical Company. So today, I will present about my work, which I've done during my postdoc. That we will see now. I will start to speak about the quantum revolution, the history. Then in the next slide about the quantum computing applications, and afterwards I will explain about the delivery of the quantum learning machine, all the details, why it's so powerful, and then I will explain about the OpenVQE package which I created, and then I will speak brief tutorials to you people, students, engineers, in order to know and to get you to know the knowledge about the tools which I've used in the quantum chemistry computation. So in this slide, I'm gonna explain to you that the history of quantum revolution, particularly in the context of the quantum information and Shor algorithms, showcases the transformative power of quantum theory in computing and cryptography. Here in this slide is a timeline highlighting the key developments. So Feynman in 1981 and his colleagues have proposed that the quantum physics can be exploited to process to process and transmit information in fundamentally new ways. Then afterwards, in 1984, the quantum cryptography has been established. Why? Because the quantum key distribution method have been proposed by the scientists, which is defined as the secure communication based on the principle of the quantum mechanics. This has been the Mark's starting point of the quantum cryptography. Afterwards, the mathematician Shor's mathematician has proposed that the possibility to show the evolution of quantum computer. How? Because he invented an algorithm to efficiently factor a large integers. And here is the breakthrough of the quantum computer, that it can exponentially be faster than the classical computer in solving really complex problems. Afterwards, at the end of 90s to the 2000s, there have been a kind of demonstration on the experimental quantum computer. So researchers there have demonstrated successfully that some quantum algorithms in cryptography and quantum computing have been successfully implemented in the experiments. And there have been a kind of great developments. Then there have been a kind of race in the quantum supremacy. And the key point was there were key players as academics and institutes who have paid a lot of money in order for the researchers and the development in order to continue the development of the quantum computing. Over the last decades, there have been a significant progress in the development and the building of the scalable hardware quantum computer. And here there are a lot of companies, as mentioned there, and including Microsoft, Rigetti, and Google. Up to 2019, Google has claimed that they showed a quantum supremacy. And here it was an advantage of the quantum computer. But there has been a debate that is still for a small real system. And we need really nowadays a kind of real application of the quantum computer. That's why we have ongoing progress in both the experiments and in both on the development of the software. So the quantum revolution is still ongoing, and here is the key point, that they are continuing to drive the innovation and the creation for the intersection of quantum science and the quantum theory. So where are we now? We are now in the NISQ era. So the NISQ era, it's a noisy intermediate scale quantum era. In this era, there are the quantum processor units, which are subject to many noise, and therefore we have limitation in the number of qubits, few hundreds. IBM in 2016 have offered 5-qubit processor, and then afterwards there have been a lot of a lot of continuation and progress in the development. Google, Intel, D-Wave, Rigetti, Honeywell, etc. in the USA, and in Europe, some startup companies in France, IQM, Pascal, AQT, Candilas, C12, Alice and Bob, and some companies over all the world, and in Asia and in Canada, etc. So there have been a lot of development. At the same time, Atos, which is evident call now, they delivered the quantum learning machine in 2017. What they deliver a quantum emulator. What is the meaning of emulator? Emulator is a tool that can allow the researchers to mimic the behavior of the quantum systems without using the quantum computer, just using the classical computer to simulate qubits. So we will go further in the next slides about the description about the quantum emulators and then about the QLM machine. Of course, there have been a lot of significant progress in the software part. For example, NVIDIA, Microsoft, as some of you knows, and other companies who are delivering startups, delivering about a lot of services for softwares. What could happen in 2026, 2027, 2028 is the question to see the quantum advantage over some applications, which I'm going to show you on the next slides. And is there a lot of error corrections? Because nowadays the NISQ devices are really subject to errors, and we need to find error correction mitigation methods in order to have a 99.99% in the future a high fidelity of 2-qubit gates, which I'm going to explain to you also during the slides. So what could happen above 2030? Shall we have millions of logical qubits, millions of qubits quantum hardware, which we call it the fault-tolerant quantum computing era? And this is perfect because this is the dream of the companies in order to be in this era, to have a perfect quantum computer with 0 errors, at least. So now about the development of quantum algorithms. As we have seen here, I just spoke on the first slides from 1985 to 1996, but then there have been a revolution about quantum algorithms for big data environment. So quantum machine learning, HHL algorithm for the quantum phase estimation, quantum state preparation have been investigated. Why? Because we need to see how the NISQ devices, even though they are limited, we need to see how they are important to show some performance over the classical computer, even for some certain tasks. So there have been a lot of work for important quantum algorithms for the NISQ era. For example, hybrid quantum algorithms. The hybrid, I mean classical and the quantum at the same time. So they are based on the variational quantum circuits, variational quantum eigensolver. This VQE, we will explain it in detail in the next slides. And quantum approximate optimization algorithm have been also explored after 2014, I guess 2015. And then now there are a lot of progress because there are a lot of researchers are trying to find versions of VQE or new versions of QAOA to apply them on the real quantum computer. Now, what are the quantum applications and the current status? There are a wide range of quantum applications that companies are trying to use case for the researchers, for the engineers. For example, there are the quantum computing application, the quantum sensing, and the quantum communication. I will focus on the quantum computing because it's the field which I'm working on in the quantum chemistry. For example, we will show how the quantum computer could help on the molecular chemistry computation in the drug discovery, in the material design, and in the machine learning. But I will show an example about the drug discovery and about the molecular chemistry, electronic structure computation. Google, as I said here, they have claimed in 2019 that they can perform an advantage over the classical computer. The calculation only needs 200 seconds over 10 or thousands of years that the classical computer will perform. As I said, it's again a debate and still under progress of this proof. Here is an example of the roadmap of the IBM, which have shown chips of thousands of qubits announced recently. And now this is their roadmap from 2019 above to 2023. And their aim is to go beyond millions of qubits and beyond. And this is a great achievement. We will see how could this help with the quantum error corrections in order to apply real life quantum computer in the future. So now let me explain what is a qubit. To know what's qubit, let's see what is bit. As you see here in the extreme left, the bit can be in a state either 0 or 1. However, the qubits can be either in state 0 or 1, or a combination between 0 and 1. As you see, we call this is a superposition. And here is the great advantage of the qubit, because as you see here, this is the mathematical expression of the qubit, which can be represented by the block sphere. So if I have theta to 0, then I'm going to be at state 0. If I am going to have phi 0 and theta pi over 2, I'm going to be at state 1. Or if they are random, then I'm going to be at superposition between 0 and 1. This superposition is important because it can allow the quantum computer to process the information in parallel. And that's very important to add also the entanglement. It's a correlation between the qubits. And here we will see that this is important, both the superposition and the entanglement in the quantum computer. Now we understood what is the bit and what's the qubit. Let's see what's the difference between the classical and the quantum processor. As you see here, there are two figures. The first one is about the central processing unit, which in the classical laptop, they are built from bits, and bits is the smallest unit of information. So if I have a data of input 0 or 1, the output will be 0 or 1, as I explained, because the CPUs, they are built from the gates, which are not 0, not or, it's just true or false, in fact. However, the quantum computer is built from the quantum processor unit, which is the QPU. So the QPU are storing qubits there. And this qubit, when an input of 0, 1, 0, then it will be 8-bit strings. That's the thing which is very interesting about the quantum computer. The more you add qubit, the more you are exponentially having more and more bit strings. So this is the formula which we use here, as we see that a CPU with n bits, we could have only n parameters. But the QPU with n bits, we will have 2 to the power n parameters, and here n is the number of the input qubits. Therefore, have you seen here in the figure, we can see that there is an exponential growth on the quantum computer, because you will have plenty of probabilities at the same time, many different states. However, the classical computer will not improve exponentially. It will stay linear, and that's the big advantage of the quantum computer. So here, very quickly, I want to show for people who are not familiar with the quantum circuits, some examples of existing quantum circuits. For example, you have seen the Intel's company, the IBM, the Googles have claimed that they constructed 49 above to 65 of IBM, then we have 72 of Google, and then they have 54. And here is the way when they claim they have the quantum advantage. And here is the real structure of the experimental quantum computer. Now let's focus on the quantum computing applied to drug discovery. Very quickly, as you know that the quantum can target small scales, as you see here in the small area. However, the classical cannot be able to perform challenges which the quantum computing can doing. As an example of quantum computing is on the lung cancer cell. So recently, with my intern student Karim El Mahdi, we tried to work on this, and we tried to figure out how can the quantum computing help to efficiently solve the problem. How can we map the problem into qubits? So it's not an easy job. We follow the process of the drug discovery, and then we followed some articles. There is something we call it molecular docking that aims to find the maximum cut solution between the ligands and the inhibitor there. And therefore, here the PDB ID, we took it from the internet, is 5ZMA. Each PDB has an ID. So therefore, here we use this incredible quantum approximate optimization algorithm, because we followed this article there, and we have seen that it can help to arise in the drug discovery. It can also make a process more efficient way to find the maximum connection between the ligand and the protein. So basically, we have extracted all the pharmacophore points from the ligands and all the pharmacophore points from the protein, and then we map it into qubit. However, it's an optimization problem. And thanks to the people who have invented the QAOA, we were able to find the solution at the end, which is the maximum solution that can be aiding the drug discovery. As you see here on the figure, here is the description of the QAOA. What happens here, we initialize the states with Hadamard gates. Hadamard gates, they can make an equal computational basis in the beginning of the state. And then we have a layer of the exponential of cost Hamiltonian and the mixing Hamiltonian. And here the mixing Hamiltonian is important because it can help to mix all the span all the solution we want for the probability of the states if we measure there. Then here we have increasing the depth. Normally, when we increasing the depth in any circuit is important, as some of you knows, into increasing the chemical accuracy at the end. So we need to measure, you need to use this circuit to measure the cost Hamiltonian. So we find the maximum cost function, and then we optimize with optimizer, which is the classical computer here, helps to optimize the parameters, gammas and betas, and then fed them back into the circuit. And then we do that back and forward until we get the minimum energy. And then we find the minimum solution, which is the one which can help for the drug's discovery. Nowadays, what are the challenges in quantum chemistry computation? There are challenges in classical computers, of course. Of course, there have been a lot of researchers. They are trying to figure out some methods that can help to find chemical accuracy at the same time improving the computation, because the classical computers, they suffer from, we need a lot of memory. At the same time, we need a large disk in order to store all the information using the classical computation methods. Again, the aim is to find a chemical accuracy important for large molecules. As you have seen here, there is benzene and there is the propane. So benzene is C6H6 and the propane is 3 carbon with 8 hydrogen. So to do the full configuration interaction to find the exact energy, we need to find all the determinants about 42 electrons distributed over 36 special orbitals, which is 72 spin orbitals. And this is needing a lot of memory in the classical computer. So how about using the quantum computer with only 72 qubits in order to get the full configuration interaction, which is the exact energy in both systems? So as we see here on this figure, we have a lot of complexity computational scales. So the couple cluster CCD3SDT, it is the triple excitation on the top of the double excitations inside a molecule. And it scales about n to the 7, which really increasing a lot. So how about computing this method with the couple cluster? We need a lot of triple excitation, and this will cost a lot the classical computer in order to perform the calculation. That's why the quantum computer for quantum chemistry is an interesting, because it can help nowadays to get the exact energy of benzene, propane, and other molecules, which are really complicated. Now let's discuss about the quantum emulator. Quantum emulator, which have been provided by Atos and now is called Evident. As I said, the emulator is a tool to help the engineers and the researchers in order to describe well and in order to integrate the quantum algorithms very well before applying into the real hardware. Of course, here is the description of the quantum machine learning, which have been provided by Atos, which is called Evident now, and the machine is called Captiva now. So what is the QLM? The QLM is a quantum computing platform that allows to write a hardware agnostic quantum programs, compiling them in compliance with the hardware specific computers, constraints, superconducting computers, ions, photonic and neutral atoms. And here is the key point, that we can also emulate them in the large scale noisy simulator, even with a large number of qubits. That's why it's a powerful emulator. And at the same time, it's possible to run this on the real QPUs, which is the real true quantum computers with a most optimal integration path between the quantum and the HPC. Of course, there are use cases nowadays where Atos is trying to have a lot of connection in terms of use case like mathematics, optimization, and chemistry with a lot of startups over all the world, including France. So what is the main advantage of the quantum circuit on the MyQLM? So one of the main advantages is that the MyQLM is a software stack, which is a free online, everybody can use it. You can just install it in your real laptop or in the cluster the local cluster computer. What is interesting is that this MyQLM can allow you to exchange with different packages. For example, you can exchange with the circ, with the Qiskit, with the Rigetti, and with Project Q. At the same time, we can only use too few lines of code that can allow you to switch quickly from the QPU of the QLM into the QPU of the real machines, like Rigetti, for example. And here is an example of two circuits, one in Qiskit and one in MyQLM. So this allows the users, the engineers, in order to see quickly how to visualize the gates in both at the same time to exchange quantum algorithms, at the same time to exchange the QPUs. This is really very interesting because I've been working on this interoperability in the QLM, and I find it very interesting because a lot of enhancement and a lot of quick answer exchanges can be between software engineers. So now about the QLM. The QLM, as I said, is a powerful simulator because it's a quantum computing platform that allows to program circuits, allow to use libraries in quantum in order to make versatile communication and in order to apply jobs like observables and others. QLM, as I said, is consisting of a software package called MyQLM, which is free online. So this package, it's a software stack that can allow to program, to simulate, and to optimize the circuits. It comes with a basic noiseless simulator and basic plugins. These basic plugins are sophisticated jobs that can allow you to do differentiation, gradients calculation, whatever the user wants. It depends on the user what he wants to execute on the real QPU or in the QPU. And as I explained in the previous slide, there is a model that can exchange with different packages. MyQLM comes also with a model MyQLM fermion. MyQLM fermion, from its name, it's related to the fermionic Hamiltonian, to the spin transformation from fermion into spin qubits, and other tools like trotterization we will see in the next slides. MyQLM can be installed in the laptop, but there is a problem. If you want to simulate large qubits, then you are not able to simulate them in your laptop because it depends on the RAM you have. Therefore, an SSH access to the real QLM appliance, which have larger memory, is important. So basically nowadays, the QLM, they have about 41 qubits in a double precision with a state vector simulator of about 48 terabyte of memory. But also QLM could come with advanced software, specific software, advanced noiseless simulators that can simulate above 41 qubits, like the matrix product state, for example, and which is very important to reduce the memory and to get more calculations. Advanced hardware models, advanced noisy simulators, whatever gate-based or analog, advanced compilers, and advanced tomography, and advanced error mitigation methods. So here I'm gonna show you in the right that the QLM simulator or the MyQLM provides a versatility, or we can say it's a powerful way how to manipulate for the user, how to define the program easily, the number of qubits easily, to allocate the qubits, and then you apply your gates, the Hadamard, the CNOT, and you just apply it to QProg, and then you display your circuit, which is the Bell state. We will see this tutorial very easily in the next slides. Now I will speak about the OpenVQE package, which is the project I've been working during my postdoc. So here, this package has been published in Wiley. I advise everybody is hearing me really to read this paper because it's very interesting. It explains the variational quantum eigensolver in detail, the comprehensive review of the methods of quantum chemistry in details, and it explains the QLM machine in details. So I advise you guys to go there and to read when you are free. Also, we use the OpenVQE with another application, which we will show in the next slides, about adding triple excitations in the top of the unitary coupled cluster, single and double, and it has been published using the OpenVQE. So here, OpenVQE is newly designed because it is related to variational quantum eigensolver that can target the ground states and the excited states of the molecule, which is the variational quantum deflation. Here, we use the QLM library. It has full compatibility with the free open source MyQLM, MyQLM Fermion, and it largely extends the capability of the QLM with up to 40 qubits using the state vector simulator. As I said, we also can create a class which have been already created, but we can improve using classes to exchange the versatility between other packages like Qiskit, Cirq, Pinalin. And here is the interesting thing, as I say, to exchanges, softwares, and algorithms between researchers. Why we need OpenVQE? Because OpenVQE is important in tackling really large molecules in the future. Because we really need important methods like unitary coupled cluster, because it can control and maintain the chemical accuracy. That's why it is important for large scale molecules, and that's what we need for making the quantum computer showing an advantage over the classical one in the near future. OpenVQE, this is two things. On the right, they have the structure, which I've created recently, last 2 years, and it is really made up of notebooks, and it's made up of 3 models. As you see in the folder, we have a family of UCC. On the right, we have a family of adaptive VQE, and we have here common files. So here we can have just easily, simply the user can say, I want to get the energy of my molecule. Then you just have to press the type of the method you want. At the same time, for adapt VQEs, which are versions of VQE, which are important because we need to see the importance on the NISQ devices, so we have to have new versions, so the user just have to name the name of the algorithm wanted. The common files are very interesting because there's a factory of molecules which can allow you to get the Hamiltonian, to generate the cluster operators, to generate your excitation, and to generate your circuit you want. So the user can use that, just have to install the OpenVQE from online, and then easily he can start to play with the circuits, can start to create his own circuit following a lot of references. So our plan in the quantum algorithms implementation is to find optimization algorithms which are really important to control the circuit depth. Because as I said, the NISQ devices are subject to large QPUs. So we have to reduce the number of CNOTs, the number of the number of qubits even, as much as we can, at the same time to have a control at the highest level. Then we have to maintain the chemical accuracy, so we have to figure out new versions of method that can be compatible with the control of the circuit depth. Why again? Because we need to benchmark molecules and to apply them in the GPUs and the CPUs. So now it's OpenVQE tutorial. Allow me to invite my internship students who work at Qubit Pharmaceutical, Hobin Tran. And Hobin is gonna explain to us a little bit about the tutorial. He will help with us because he is a stagiaire student and he was able to use the tutorials very easily and he created them with me. So that's why he will help us. Can you, Hobin, say hello to everybody? Yeah.
Hello, everybody. My name is Weaving. It's nice to meet you guys.
Yeah. So, Hobin, just a second. I explain this slide and then we will move back to the tutorial.
Yes.
Okay. So here, as you see, guys, the VQE, Variational Quantum Eigensolver, in 2 panels. There is the top panel and there is the bottom panel. In the top panel, just we use the tools of the QLM. So how to initiate the geometry, the basis set of the molecule, which able to calculate the 2 and 1 body integrals, and then to transform the Hamiltonian into qubits, to use a lot of approximate method, active space selection, conversation to qubits, because we need the system into qubit language. Also, we need ansatz construction, so we will come back to that later, and to define the job. The job is the circuit plus the Hamiltonian. As soon as we define the job, then we come back to the bottom panel, which is the QLM stack that can take care about that. The QLM stack can come with no plugins or come with plugins. What I mean by plugins, that we need sophisticated jobs. As I say, we need to find a sophisticated job that can take care about the variational algorithms, which are important for the NISQ devices, or to compute gradients, or to make orbital qubit ordering and to optimize the depth, etc. So there are different type of plugins like compilation, like observable splitter plugins, which are really sophisticated and very optimal in the code. So there is no time complexity of the algorithm and it's very easy to use them. So it depends on the user how he wants to execute on the QPU. If you want to execute with a minimal job without using any plugin, then you can apply them directly on the QPU, just transforming your Hamiltonian into z-axis, and then the QPU will return you back the optimized parameters, which is the energy. Because this is the principle of VQE, that at the end we need to obtain the minimal energy. However, if we use these plugins, then we can use them. Of course, we show you in the next slides how we use them. And then the QPU again we will stack them on the QPUs, and then the QPUs will return the minimum energy and the minimal solution of the state vector. Of course, as I explained, there are different type of noisy simulators you can use. You can use different type of simulators, which are very interesting, stabilizer, Schrödinger, and PS. And there is also possibility to interact through Python to trick the QPUs like IBM, Google, and Rigetti, and others. So now we will start with the OpenVQE tutorial. The state of the art in classical chemistry, as you have seen here, the electronic structure Hamiltonian. We have three terms, 1, 2, and 3. This is the kinetic term. These are the Coulomb force, the Coulomb terms, which is coming from the Coulomb force between the electron or the electron and the protons. So as you see here on this, we have the presentation of the molecule in the coordinate system. So we have the nucleus A and B with the distance r a and b, and we have the electrons. But in our case, we are in the Born-Oppenheimer approximation. So if we want to go beyond the Born-Oppenheimer approximation, we have to consider that the nucleus are really moving in order to take the whole system in motion. And this is the expression here that describes the beyond Born-Oppenheimer approximation. However, mostly people now works in quantum chemistry in this formula for the Born-Oppenheimer approximation. Of course, as I say, the VQE is like QAOA. It is a hybrid algorithm. It's used the classical computer for the optimizer and the quantum computer for the running the circuit to prepare the parameterized state and to measure the state. So what we do, we just define the values, and then we fed them into the circuit. The circuit will measure the Hamiltonian, and then the expectation value come back to the optimizer, update the parameters, as I say, back and forth until we get the lowest expectation value of the Hamiltonian. Then we will see how the OpenVQE tutorials work. We will show how the Hamiltonian as an observable class can be created. It can be other observable, Hermitian or non-Hermitian. We just have to create a class which can help, which is called term, that can help to define the linear combination of the Pauli strings, find if I, X, Y, Z, X, X, which with their coefficients, CKs, in order to store them in the term and then to implement them in the quantum circuits. Another example is to show the Ising model plus the hardware efficient ansatz. So we have different ansatzes now which are circuits. This is the formula of the ansatz, which is based of layers of Rx gates and Rz gates, which is not a static, it's variational because we have thetas. That's why we have to use the optimizer in order to update the parameters and then to get the minimum energy. Here is the Ising model of the Hamiltonian of two parts of X and Z's with I opposed to G's. And here we will show you that the OpenVQE can help to run this algorithm with hardware efficient ansatz using the Ising model, and then we will show the minimum energy at the end with using a lot of iterations. Based on the optimizer you are using, there are two types of optimizer, non-gradient and there is the gradient. So for the gradient is more simple and more beautiful, but it will need more and more iteration. However, Atos also, they have created a plugin, we call it the gradients plugins, that is able to minimize a lot the VQE iteration. So there are a lot of possibilities to let the gradient-based optimizer works very well. We will see that on the next slides, how to run this Hamiltonian, the circuits, and to get these results on the tutorials. So again, we have this Hamiltonian, we represent it into the second quantization of the one body and the two body integrals, and then we have the single and we have the double excitations. P, Q, R, S. These are the spin orbitals where the electrons can jump one level into another, and these are really at the maximum number of qubits. So here is a small script how to implement this Hamiltonian. We just import from cat fermion electronic structure Hamiltonian, and then we fill the HPQ, HPQRS as matrices, and then we just call the electronic structure Hamiltonian, we put the coefficients, and then we generate our Hamiltonian as a linear combination of the first and second single and double excitation, let's say. But as I say, we need to transform the language of fermionic into Jordan-Wigner, and therefore we use the Jordan-Wigner transformation. Again, we just have to simply put this name Jordan-Wigner, and you obtain a linear combination of your Hamiltonian in a spin transformation and as a linear combination of X and Y and Z. Okay, OpenVQE extends that. OpenVQE came also with a unitary coupled cluster wave function. So the coupled cluster wave function is just an exponential of excitations applied into the Hartree-Fock state. So these are the excitations, are single and double. But OpenVQE add triple. As we see here, we claim to find that UCC as dt is a single, double, triple, and then I added all this excitation, added the new terms. As an example, beryllium hydride, it's a 6 electron over 7 spatial orbitals, which are 14 spin orbitals. BH2, if I make a single excitation, it's easy. Double, I just move the two, I jump 2, I create them there, I annihilate there. For triple, I create 2 there, and I annihilate there. So we have to be sure about the spin symmetry and the point group symmetry there. Because if I don't put these symmetries, I will have a lot of parameters to optimize. And therefore, the gates also will be a lot, and this will be a problem to run them on the real quantum computer. We need accuracy, but the problem is that the ansatz, as you see here, it's really very huge. A lot of number of CNOT gates, a lot of 2-qubit gates entanglement, and that's the main error in the quantum computer for quantum chemistry. Therefore, I tried to impose the point group symmetry and the spin symmetry and the particle conversation, which is easy because it's fermionic, and then I generate all these excitations using the spatial symmetry and the spin symmetry. So it's easy now. The users can go to add the symmetry he wants, and he can launch whatever molecule he wants in the abelian group symmetry. On the next lecture, maybe we can go to explain to you guys how the symmetry works and how it really can help a lot to reduce the number of parameters. As a result, we publish these results and we show the comparison between the triple and the double excitation of UCC, beryllium hydride again. The blue line is the chemical accuracy, which is the one in the 1 point something 10 to the minus 3 for reaching the chemical accuracy. And here is the error. The error is the FCI minus the energy from the VQE. As you see here, the black stars and the red stars. So the red stars are related to the triple excitations, and the black are terminated at the double excitations. And we see that adding more and more excitations, we will have more and more chemical accuracy. And that's in the bound 0.5 to 3.5. And these results have been tested in other molecules, in lithium hydride, water, and this is the beryllium hydride. We define the number of qubits, we define the point group symmetry, we define how much parameters have been reduced after using the symmetry and how much percentage have been reduced, and comparison between the double excitations and the triple excitations. And as a conclusion, for these simulated molecules, we find that more than 2 orders of magnitudes of accuracy with respect to double excitation have been improved. OpenVQE also comes with excited states. So the user can prepare initial states which are orthogonal to each other, phi 0, phi 1, phi 2, up to k excited state he wanted to terminate. You want first excited state, second excited state, third excited state. It depends how the user he wants. So we generate an algorithm that is general for the user in order to mention which state he wants and compare with the diagonalization of the Hamiltonian. We have three steps, sorry. One is finished. Second, for each of these states, we apply a unitary gates, which is the quantum circuit. To generate these states, in fact, and it's easy just by this expression. And then we need to use the VQE algorithm. We propose our cost function that it is related to the Hamiltonian by himself, plus adding the weight, which is Wi. It depends on the weight. You can, of course, know which excited state you want to target. So the weight can be 40, 45. So the user have to play with the weight. So it's an optional here also as an input. And then you just apply the VQE stack and you optimize, you minimize. At the end, you get your minimal energy, which is related to the first ground state for the first excited state or whatever case state you want. As an example, hydrogen molecule. Hydrogen molecule here is the ground state. Here is the first excited state, and here we have the second excited state, and here we have the third excited state. So here we have to be careful. The ground state, there is no degeneracy. But for the excited state, first excited state, we have S equal to 1. So it's a triplet state because we have the projection over the z-axis -1, 0, and +1. Here, this is the source from Pinelin, but we are able to execute it using OpenVQE tutorial. And we use the VQD algorithm. And we were able to arrive to the results from the left to the right by using the VQD, and we got the minimum energy, the first excited states, which are 3, because 1, 2, and 3, and we also have been able to arrive to the second excited state. And that's the beauty, because it's now already very compatible and in a very short code that allow the user to invent new results in the future if he wants to work on the excited states. Point group symmetry, as I explained, we have single, double, triple, but as I say, we need a lot of parameters to optimize if I add the triple excitations. Therefore, to reduce that, we need to add the molecular symmetry. When I say molecular symmetry, it's simple. You have to pose the abelian group symmetry in your molecule to see how it rotates, how is the reflection, and how is the inversion, and how you apply the identity. Then you can be able to exploit the point group symmetry. As an example, you see water, H2O. We are able to use our ORCA algorithm to run them. We need first to initiate our geometry, the XYZ, and then we were able to define the irreducible representation of the orbital we want. Suppose this is an orbital 2. So we have here on the right the molecular orbital diagram of water. On the left we have oxygen, on the right we have the hydrogen. So if I use the SALCS, then I am able to make a linear combination between the oxygens and the hydrogens, and I'm able to obtain all the molecular orbitals of the water. And here on this, we have 10 electrons are occupied over 7 spatial orbitals, which is 14 spin orbitals in the STO3G basis set. Because each molecule, you can apply the basis set you want. Here, there are different types of geometries, and I guess here we just have to use the ORCA to target which excited state we want. We want this, or this, or this. We call them the HOMO and LOMO, which is the highest occupied and the lowest occupied. So now we will briefly explain with Hubin you can come, Hubin. We can explain a little bit the tutorials, and then we will end the session with questions with you guys. So do you see the screen, guys? Okay. So here, as an example of the basic OpenVQE, as I say, we are compatible with the QLM. So we need to code this Hamiltonian, for example. We just need to import the classes term and observable. So this is an observable. We just have to initiate the class, and we initiate the number of qubits, 2, 3, 4, whatever. And then we will use the Pauli terms. And here it's just you have to print it out, and then you arrive to your result. Now, there are also, as explained, different ways how to apply the stack of VQE you want. So there is a generator of job after applying it, and then you execute it in the QPU. The QPU will return back the amplitudes and the state vectors. So for example, if I want to create the bill pair state, so here I will have a program, and then I am going to have the number of the gates I want to initiate, and then I will have to say what are the number of qubits I want. Then I allocate the number of qubits, and then I initialize the Hadamard and the CNOTs. Afterwards, I say what is the circuits needed, and then it's displayed. And then what is the QPU wanted, which is the QPU for the state vectors. And then I apply the job, and I just put the number of shots wanted, and then I submit the job. And afterwards, I can be able to get the circuit. And here are the amplitudes which are getting from the bill state, the 0, 0 and 1, 1 of these amplitudes. Now, if I want to use the advantage of the interoperability, we can be able to move from the QLM to circuit or circuit to QLM. So you can import just Qiskit, import QLM to circuit. I want to translate my QLM circuit into the Qiskit very easily. You just have to initiate the circuit, and then you can put the circuit in the QLM, and then you draw it, and this is in the Qiskit. And that's the beauty of the things, because you can visualize different type of circuits. Here, very easily for people who are not familiar of the universal gates, so we have different range of gates, so you can easily go to the dictionary and you can see the name of the gates, and then you can import them and you define the number of qubits, and here the visualization of the matrices you want. Of course, here is the way how to play with the manipulate with your circuit, and then you can just apply the gates, and then you display your circuit, and it's easy to apply. The variational computation, as I say, we are going to execute the minimum energy of the Ising model. So very easy. We just have to define a function, Ising model function, and then the terms in order to implement these terms. And then we generate the terms and their coefficients here, A and J. And then we are able to append them, and then we obtain the observable, and which is generating for us the Ising Hamiltonian. Therefore, the user have just to mention the name of to mention the number of qubits, and mention the class and the number of qubits there to derive the linear combination of Hamiltonian. Then, of course, here we can have a way how to apply the ansatz. So we have a different class. We apply the hardware efficient ansatz, which is a circuit that can be a combination of gates and can be a combination of parameters, because we need to optimize. So it's very easy. You just make the parameters variable, and you can apply them in your gates. And therefore, there are different loops here to construct your circuit. And here, the user has just to implement the number of layers he wants, and using the class with the number of qubit, number of layer, the gates wanted, and the CNOTs. And here is the hardware efficient ansatz, how it works. As I say, VQE with the QLM comes with different stacks. So if I have the job of the circuit, and then I have the stack of the optimization, then I stack it on the top of QPU. And then here, when I have the circuit and the observable, I can use this plugin in order to get the minimum energy, and then it return back the minimum energy. Very easily here in this cell, as you can see there are two types of codes. There is the definition of the QPU you want, and then the SciPy minimize plugin, and then you just define the optimizer you want, and then you can initiate your parameters, and then you stack your plugin on top of the QPU very easily, and then you submit your job, and then you get your minimal energy. Of course, we can go beyond the hardware efficient ansatz. We can use the unitary coupled cluster. What is unitary coupled cluster? We need first to get the minimum energy of the Hamiltonian. As I said, it's an exponential of excitations applied on the top of the reference state. Then these are the excitations, and then we have to code these excitations. What happens? First, I have to define the geometry of my molecule. So I am working with a hydrogen molecule, so I have two hydrogens, and then I have to use the PYSCF method package in order to initiate my molecule. And therefore, there are different type of properties we have to encode, and then we were able to get a lot of properties back, the Hartree-Fock energy, the FCI energy in the dictionary. And then you can define the number of qubits you want. So here is the way how the number of qubits before any active space selection, no frozen electrons, nothing. So it's only four qubits we are going to work on. Then afterwards, after I have my molecular Hamiltonian, I have to apply these one body and two body integrals, and then I can generate my Hamiltonian using this class. Now the computation of the cluster operators and the good guesses of theta 0 is very easy. You just have to use simple functions as written here. Get the cluster OPS, which can help you to get cluster OPS. You define the number of the electrons and you find the number of qubits, and then you initialize, and then you get afterwards your Hamiltonian here, and then afterwards you get your cluster operators, and then you apply your trotterization because you want to cut the exponential into products of exponentials, and you apply your circuit, which is the UCC circuit, and you can display it there, which called it construct UCC ansatz. So to finish soon, now we are going to apply the job as I say, and we are going to use the circuit, we use the observable in the spin Hamiltonian, and then we use this stack, which is the optimizer psi pi y, to define the optimizer, the tolerance you want to get the energy, and the maximum number of iteration you want, and you initiate the parameters. Stack optimizer psi pi y on the QPU get default, and then you submit your job, and then you get your minimum energy. So here is a range, is the minimum energy we got. For example, you need only 35 steps to get your converged energy. Now, how about plotting the energy with respect to inter-atomic distance? So you can just define again the hydrogen molecule. You say you want it from 0.5 to 3.5 angstrom. So you can stretch the hydrogen with distances more and more, and then you can apply the same one, and then the results is easy. As you see here, from 0.5 to 3.0, you can obtain the minimum energy, and then you can compare with the classical chemistry methods from VQE minimum energy and the other energies. So now you can run also the demo of OpenVQE. As I explained here, the OpenVQE, I will explain the UCC family very easily. You just have, it's very sophisticated with really new methods and new functions. You can just make a factory of molecule. You can get your parameter. The user have to put the name of the symbol of the molecule, and it will return back the geometry, the charge, the spin, the basis. And then you can generate your Hamiltonian, the spin Hamiltonian, number of electrons, the newns and the orbital energies, and the info. You just have to say, I need active space or no, and which transformation you want. And then you initialize the number of qubits, and then you get your cluster operators by applying this generator cluster OPS. And afterwards, you just have to return back the pool, the excitations, and you have just to use this sophisticated get energies that allow you to get the energy of UCC at the end. And here are the results. It can show you all the results you want in a very classified way. So before finishing, 5 to 10 minutes, now the triple excitation, very easily, we generate a very interesting function. We can say generator excitation, import the triple excitation, and apply the transformer you want. And then you use the symmetry there. You just have to put it in the common files so the user can easily access to the orbital symmetry, can include the point groups and the sub-point groups he wants, and then he apply the triple excitations, generate them based on the number of special orbital and the number of electrons, and then you say you want symmetry, you don't want symmetry, it depends on the user how he wants, and then it generates the orbitals, the operators. You can put the name of the molecule, the number of occupation, the number of special orbital, you apply your symmetry or not, as I say, apply the transfer or not. And here at the end, if I print out the number of operators in lithium hydride, it's 24 operators after using the point group symmetry. Of course, if I want to compute the excited states, it's also here very easy because there are sophisticated functions that allow to OPT function that allow to obtain the excited states in a very easy way. And the users can easily ask me if you want, we can negotiate in the future and discuss how to get the excited states. And therefore, we apply them, we get the energy for k equal to 0, 0, 0 because we are looking for 4 qubits for hydrogen molecule 0001 or 1011, and then here you are targeting your states with a fidelity 1, almost 1, almost 1, and that's why we get the minimum energy of the first 3 excited states with their fidelity is equal to 1 almost. And here we are continuing now into the corrections of the minimum energies, because we have to add more and more energies and more and more classes on the OpenVQE package. So now I return back to the Hubin, you can return back now to the, you turn me back to the slides. Yeah, it's there. Is there? Thank you, Hobin. So at the end, now to finish, really, guys, it's very important for us. If you want to help us, you can contribute to the OpenVQE package. Here is the website and the GitHub, and we would love you to make star there because we really wanted to contribute that with Quantum Computing India. To thank a lot Quantum Computing India for helping us to advertise our package and to see how this package works. So we would love you guys to really visit this website in order to make star, and we will be happy to work together in the future because it's an open source package and to develop it together. And that's why I want to conclude OpenVQE is a newly designed package in quantum computing for quantum chemistry. Contributors over all the world are welcome to advance together the state of the art of quantum computing. We would love to build a project, organizing workshops and making public interaction together. So please reach me, guys, by my email or my LinkedIn there to contact me. I am also free to meet up and catch up through LinkedIn and make open questions to collaborate together and to publish if we really think we can create new algorithms using OpenVQE package. So I want to acknowledge a lot Total Energy, Atos, Sorbonne University, and Quantum Computing India for this invitation. Very, very nice of you. Thanks. And I would love also to thank Qubit Pharmaceutical for this presentation. Thank you.
All right. Lovely. Yeah. Thanks a lot, Dr. Mohammad. It was really enlightening. I learned a lot personally, and from the looks of the messages that we are getting, people have learned a lot as well. So we'll start with questions. Let's take 10 minutes to answer. Let's see how many we can answer.
Yeah, please.
Okay. So I'll start with the questions that people have asked while they signed up for this session.
Yeah.
So one is, okay, we are calculating only about 1% of total energy in the form of PF correlation energy using quantum computers. Is it really worth of showing quantum advantages in chemistry? And also, is it possible to simulate large molecular clusters on the current state of quantum computers or quantum simulators?
Yes, so I would love to show you, thank you for the question first. I would love to show you this. Can you, Hobin, show me this slide on?
I'll also put up the question in the chat window for people who have missed the question. So this is by Deepak, by the way. Yeah.
Yeah. So in fact, this is the slide which can answer the question of this guy. So we have to know that quantum computer, there is no advantage yet. So in order to show an advantage, we have to show that something is not really clearly feasible on the classical computer. As you see here on the right on the figure, at 30 electrons and 30 special orbitals, which is 30 spin orbitals, which is 30 qubits, we can start to see that the quantum computer can show an advantage. Because the classical computer at this level is unable to show to make the calculation, in fact, because we need the FCI energy and the classical computer is unable. That's why here is the way that the quantum computer is able to show the advantage. But for the time being, there is no real proof that the quantum computer can show an advantage over the classical computer. That's why people and researchers are ongoing on the research to make active space selection, like complete active space selection, in order to target these qubits and to see what kind of algorithms that can efficiently help to show the advantage on the current NISQ devices. But because the current NISQ devices are limited by the number of qubits and a lot of large errors, so we still have a lot of manipulation to do to reduce the number of CNOTs and to control the circuit depth at the same time to have a chemical accuracy.
All right, lovely. So I'll start reading questions from the chat here. Okay, so I've seen you showed example about hardware efficient circuits, but you don't show it on chemistry calculations. Is there any difference between them?
Yeah, that's a very nice question as well. Thanks for the contributor, the guy who wrote it. In fact, my goal was to show that OpenVQE is really targeting molecules to reach chemical accuracy. But the chemical accuracy is very important. But the hardware efficient ansatz we can use in the chemistry, the hardware efficient ansatz, but they are lacking the symmetry. They are lacking the property, a lot of properties to apply on the real quantum computer or the quantum computer. That's why we use the UCC, because it's chemically defined and it's chemically accurate. That's why. Yes.
No, continue. No, continue. Continue, doctor.
Sorry?
No, you can continue. I think it was misspoken. Someone unmuted themselves by mistake.
So you want me to repeat?
No, you can continue.
Yeah, and therefore both can be used, the hardware efficient ansatz and the unitary coupled cluster ansatz. But basically, people who are chemists, they would love to work in the UCC ansatz approach because they provide more accurate results. But for the hardware efficient ansatz, it's manipulation by hand, and so it needs a lot of careful manipulation in the gates and in the imposing the symmetry in order to get a chemical accuracy. So basically, personally, I would prefer the UCC because they provide more accurate results.
Okay.
But OpenVQE has hardware efficient and has also UCC.
Nice. All right. So this is by Bashwant. He says, I'm a researcher working in quantum chemistry. I was wondering if you can throw some light on whether it is possible to do FCI approach using phase estimation algorithm on NISQ devices available today. So that's one part of the question. The second is for each measurement on quantum computer, you get one energy and associated wave function. Then let us say if one is performing 1,000 shots, then do you take weighted average energy?
Then I take what?
Weighted average of the energy states, of the shots, basically.
Yeah, so to answer the first question, of course, the quantum phase estimation is a very interesting algorithm for the fault-tolerant quantum computer. However, I would say it would be possible because if you are using, for example, UCC ansatz, then you can minimize your cost function. At certain level, you can cut it, and then you can say, I wanted to apply the quantum phase estimation exponential of tau into the Hamiltonian, and then I am able to cut there, and then I am applying this state directly using the quantum phase estimation. And this could be helping a lot, but I haven't tried it, but it's a very interesting question, and I think it can be applied soon. It depends on the ansatz you are using. So if you are using UCC ansatz, you are arriving at certain level, at certain chemical accuracy, then you can use a shortcut quantum phase estimation, and then you can arrive directly to your answer. But for the time being, I haven't seen somebody really working on this in this approach. For the second question about this, the number of shots, right? This is the question.
Yeah.
So then and the question is to understand exactly.
You want me to read it again? Yeah. So for each measurement on quantum computer, you get one energy and associated wave function. Then let us say if one is performing 1,000 shots, then do you take weighted average energy?
Absolutely. So if you make 1,000 shots, then we make a weighted average. We sum all these expectation values of the Hamiltonians, and we sum them, and then we get the optimizer to get back the energy, and then we update the parameters. So it's really, if we have thousands of shots, the circuit will measure the expectation value and add the sum of all these expectation values.
Okay, cool. So just two more questions. So one is how to model the inorganic fertilizer composition using quantum chemistry related stuff.
Sorry, I didn't hear your question very well.
Yeah. How to model the inorganic fertilizer composition?
Yeah, I would say I don't have a lot of expertise on the organic stuff. I was giving an example about molecular docking, and I think there is no yet work on this approach because it still needs a lot of qubits to do. So as I say, the quantum approximate optimization algorithm is a simple algorithm that can work on the optimization problem of drug discovery for molecular docking. And therefore, I would say organic molecule, you need a lot of qubits unless we use active space selection, but it has to be carefully understood in order to define the system first, and then we can use literally little by little the DFT and the Hartree-Fock and then the post-Hartree-Fock methods in order to see which method can be applied first, and then we can formalize the wave function we need.
All right. So next is by Akash. So is it possible to replace the DFT Hamiltonian in the place of Born approximated Hamiltonian in VQU?
Actually, it's possible because there are some recent research. They use the title of the name is How Applying the Density Functional Theory on a Quantum Computer. So I've read a little bit about this article and it's very interesting. When we say DFT, I didn't understand if he means by the Hamiltonian, but I think it's possible to do a DFT for a wave function. So this, I think, what he means, and therefore it's possible. Yes, I can forward the article to the guy who asks, and then we can show him how it's done. Of course, yeah. But as I said, the DFT, it's really not very accurate as a coupled cluster, as we see on the curve. And that's why DFT it can be applied compared to the Born-Oppenheimer approximation, but we still need a lot of careful discovery in the DFT, of course, first.
Okay.
To get a chemical accuracy.
All right. Yeah. So guys, so the deck, the notebooks, and the video, everything will be shared with you. Okay. All right. Gaurav, yeah, you can unmute yourself and ask the question.
Hi, am I audible?
Yeah.
Hi, this is Gaurav Banerjee. I'm working as a quantum computing digital practice as a COE. Last 1 year, I've been studying quantum computing from IIT Madras. So I have a question to you that for optimization kind of problem, if I say specifically, like portfolio optimization, 3D bin packing, and there are a lot of optimization problem out there. So you mentioned about QAOA, right? That is one which can be solved using gate-based quantum computing. But we do have quantum annealer as well, right? Which is doing QBO and other kind of stuff for optimization problem. So as of now, do you have any proof which is saying that this optimization problem is performing better than classical optimizer like Garobi, which is mostly used in all industries, then Cplex? These are the most powerful optimizer right now available. So do you have any proof like maybe QA or quantum annealing which can work better?
Yeah, I actually thank you for this very interesting question. Actually, as you see, QAOA has been really used on the quantum molecular docking. As I said here in this article, there are a lot of proofs that they tried to solve optimization problem, but I don't have a proof that it's really better. It's giving an advantage over the classical computer. And therefore, of course, we have a lot of optimization problem, but I've seen in this article, they are trying to even include one more layer in order to make it as a driven optimization method. So I think they are adding cost Hamiltonian, mixed Hamiltonian, and I added also another layer that can enhance the optimization. But there is not yet a complete proof that the quantum approximate optimization algorithm showing better than the classical, because there are limitations, as I say, in the NISQ devices, and therefore we really need to be careful about the error corrections there. And there is just a question of how to use the combinatorial optimization problem using QAOA. It's really working well, but it's not really giving a great advantage because we are still limited by the number of qubits. For example, in the cancer lung, when we worked, we only have 40 qubits at the end, but then we use active space selection sector in order to reduce more the number of qubits. And reducing the number of qubits, then it can be feasible again in the classical computer. So that's why we really need to increase the optimal calculation. We really need more efficient emulators that can be able to help us to emulate 40 qubits first, which is not very easy. And then we apply QAOA, whatever the optimizer you want, and then you can check it on the quantum computer. Again, noise study is very important, like error mitigation and so on in the QA, for example. The same thing for quantum annealing, because it's also specialized quantum computing approach that aims to solve optimization problem by exploiting quantum fluctuations. But as you know, the quantum annealing is really starting in quantum superposition of states, representing possible solution to the optimization problem. And it also even including the Hamiltonian that is really slowly varied over the time. And I've seen two articles recently. One has been published by Pasquale in Paris, which have been really applying the molecular docking problem using the neutral atom analog systems. At the same time, I've seen an article that has been working also in quantum annealing, but I cannot tell you that there is really a great advantage on the quantum computer
So,
yet.
just a follow-up question. So this QAOA or VQ we are using for molecular docking and all these things, right? Finding out the ground state energy. Can you
Yeah.
use this technology, like use this framework, leverage it to solve for other kind of problem statement, like for any other optimization problem, general optimization problem, or is it only as of now limited to the only molecular or quantum chemistry? That's my doubt.
No, it's not only for molecular. If you have an optimization problem related to network, for example, you can impose it as an optimization problem. But solving combinatorial optimization problem is not only related to QAOA. We have an algorithm we call the QPO. This QPO, it's really a very interesting one.
Yes, yes. I have used it, but it is for binary optimization. So only if your variable are in binary in nature, then it is fine. But in real life, it is not, right? It is floating or integer kind of stuff. That's another issue. Yeah.
Yeah, exactly. So, but I've seen another article very recently. They are testing all the classical optimizer once a time. What is copula, what is BFGS, and so on. And they are trying now to enhance the optimization. I can forward you the article, and they show how much function evaluation can each optimizer need in order to get the minimum energy per QAOA or quantum annealing. And indeed, there are Adam optimizer. There is also stochastic optimizer. So there are a lot of optimizers they have been using, and still the key point is that you have to compute the gradients, because some optimizers are based gradients, and then you have to use the circuits which can compute for you back the gradient. And this is additional cost into the CPUs and the QPUs. That's why it's really still problematic, not only for molecular docking, but any other problem. So the optimizer is a key point. I agree with you.
Thank you so much, Dr. Mohammad. I will look forward to connect with you on. Thank you.
Yeah, with pleasure.
All right. Yes, any other questions? If not, we just have two asks from you. One is we'll be sharing a feedback form, so it'll help us understand, whether what kind of topics to cover next. And the second thing is, if you all can turn on your camera, you can all take a picture together. Dr. Mohammad wanted that to happen as well.
Can we,
Yeah,
can
so
you
first is feedback form is here.
yeah.
Okay, so that's all right. The second ask is if you can turn on your cameras, you can just take a quick picture.
Yeah, so Sam, I think he's saying that each one has to open his camera now, because we would love to take a picture all together to celebrate the India World Quantum Day and France and whatever. It's really great pleasure for me.